Well, hello, this is Mr. Tinker, and this is the first video of microbiology. And I've gone by called the name of my channel, Tink Talks. I hope you enjoy this, and this is specifically made for my students, but of course anybody can hopefully derive some benefit from this. We'll be looking at chapter 16 from the textbook, and the title of that chapter is Nonspecific Defenses of the Host. And we'll be looking at each of these slides, and I'll do a three-part series, and this will be part one of chapter 16. So we'll look at some basic terms, and we want to talk about immunity and how does immunity affect organisms, and how does that affect humans specifically. And some terms we'll be looking at are susceptibility and resistance. Now, susceptibility, having lack of resistance to a disease. If someone is susceptible to a disease, that means they have not yet been exposed to it, and therefore have not produced any antibodies against it. So in the current climate right now, with coronavirus swirling around the globe in this current pandemic, many people are susceptible. In fact, everybody would be. It's a novel disease, and so therefore we have susceptibility to it. We have not yet produced antibodies against COVID-19. Resistance is the ability to ward off disease. So if we have produced antibodies against a particular antigen, we then have the ability to fight off that disease, to ward it off, and our immune system will function in a way that will hopefully keep us healthy and be able to continue on with our lives without need of care or hospitalization. Two main types of immunity, and this chapter is just focusing on the first one, the nonspecific or innate immunity. These are defenses against any pathogen present at birth. These would be called our first and second lines of defense, as it's known. Responds rapidly and no memory, and so these are nonspecific defenses that we possess against anything that's coming into us at any time. This responds rapidly. That's definitely a pro for it, but it has no memory, and so therefore there's no, what can we say, recollection of a disease and being exposed to it. So that's all nonspecific, and that is what this chapter specifically, if I can say that, nonspecific, specifically looks at. The next chapter, chapter 17, is on specific or acquired immunity, and that one has memory, and we're talking about B lymphocytes and T lymphocytes and how we develop memory against these particular antigens that we encounter. So this chapter, however, is just focused on nonspecific, or it's also called innate. We are born with it. We have it innately. It's within us, and so things such as mucous membranes or our skin, we all have that, and so therefore we call that innate immunity. This just looks at it graphically. You can see there are three lines of defense, and again we'll be looking at the first line of defense and the second line of defense. Third line of defense is, again, specific resistance, and that's chapter 17. And you can see the examples that I have there, and I mentioned those a little bit ago. Intact skin, mucous membranes, normal microbiota. So we have a number of bacteria and fungi that are colonizing us, and they are what we refer to as normal microbiota. An older term would be the normal flora that live on us and within us. Second line of defense, those would be some examples: phagocytic white blood cells, inflammation, fever, antimicrobial substances, mainly proteins that we produce in response to these antigens, and so we call that our second line of defense. So this would be beyond the first line and moving further into our bodies, so to speak. And then the third line of defense, as I mentioned, B cells, T cells, and the antibodies that are produced by the B cells. There's a video there, a link on how the immune system works. It's a good one, and you can click on that hyperlink and watch a thoroughly entertaining video on how the immune system works. And it does it, a nice animation of it, shows it graphically. So feel free to click on that. Pause the video, check it out, and then pick up on the next slide. Speaking of the next slide, so we're going to look at physical factors. First one we'll look at is skin. Why is skin so effective? My goodness, it's so thin. It's only a few cells thick. But without it, we're done. It's over. So what is it about the skin? Now, there are a number of functions of skin that are absolutely essential for us to live, but we want to speak only on and focus only on the aspect of the skin that protects us from pathogens. So what are some factors or characteristics of skin? Well, tightly packed epidermal cells, they're layered over each other like scales, and they're tightly packed together in stacks, as I said, that are overlapping. It's not in a column formation where you have one column of skin cells, stratum basale cells, the whole way up to the stratum corneum. They're overlapping, and that's important because if they were stacked as straight columns, bacteria could weasel their way down through and get into the lymphatic system or the circulatory system. So it's good that they are overlapping, scale-like cells of the stratum corneum especially. As you can see, the stratum corneum is 15 to 20 cells thick. And for bacteria, my goodness, that would be almost impassable for them to get through. The cells are fully keratinized, and so they have this protein, and bacteria do not possess the enzyme keratinase, which is the enzyme that's capable of breaking keratin down. Now, fungi do, and we'll talk about that and the benefit that enzyme is to fungi later. But bacteria do not possess that enzyme, so they can't metabolize the keratin that's in these cells, and so therefore it's impenetrable to them. Skin is dry, and microbes need water and moisture to reproduce and use for their metabolism, carry out the biochemical processes that are necessary for their survival. And because of the dryness of our skin, they're not capable of doing that. And we're shedding our cells every 28 days approximately. The entire layer is replaced, the entire layer of the epidermis, and so it's shed periodically. So we're constantly sloughing off cells, and with that we're sloughing off the bacteria. The bacteria then become dislodged from us, and they go off of our bodies onto the floor to be swept up or vacuumed up if you are so inclined to clean your house, which I'm not, and so it kind of backs up. Just kidding. So it's shed periodically, and so therefore the microbes don't get to reside on us for very long. Some other physical factors we have mucous membranes. We have an enormous surface area of mucous membranes. The average person has about approximately 4,000 to 4,500 square feet of mucous membranes. And that's a pretty large surface area. I mean, think about that compared to if you own a house, the surface area to your home. You can realize that that's a pretty large surface area. I can tell you my home is not 4,000 to 4,500 square feet. It's quite a bit less than that. So we have a large surface area of mucous membranes. We have a ciliary escalator, which are the cilia, which are cell membrane extensions from the cells within our, say, respiratory tract, for example. And the ciliary escalator acts as a filtration system to capture microbes, trap them in mucus, and then transport these mucus trapped microbes away from our lungs for us to expectorate them and get rid of them. We have lacrimal apparatus that washes the eye continuously. Every time we take a blink, we contract muscles, and those muscles will cause these lacrimal glands to squeeze and secrete tears, and those tears then have a continual washing over the surface of the eye. They also, as with mucous membranes as well, mucus itself, there are chemical factors as well, but we're talking just about the physical factors for now. We'll get to chemical factors in a few more slides. Saliva, just the action of it washing across the surface of our teeth, dislodges microbes and gets them out of our mouths and off of our teeth. And then we swallow them and they go to the stomach to be taken care of there by the stomach acids that are there. Many microbes cannot survive in that extremely acidic environment. Urine, vaginal, diarrhea, vomiting, all of these secretions, microbes flow out with them. So anytime there are microbes there inhabiting there that shouldn't be, pathogenic ones, our systems will respond in some way to get rid of them. in the severe cases of diarrhea or vomiting, but just in the simple urination and vaginal secretions, microbes will flow out naturally with them, pathogenic or not, and they will leave, so they don't have the opportunity to reside there for very long, build up a biofilm, and then create illness within us. We have large coarse hairs in our nasal passages that are covered in mucus, and they will also trap microbes. So try to breathe through your nose if you can. It's a natural filtration system, and it's a way to trap microbes better than letting your mouth hang open like a fish and breathing in that way all the time. Closed mouth, breathe through the nose. Unless, of course, you're congested, then I don't recommend you do that. The lower respiratory tract has a ciliary escalator, as I mentioned. As you can see in this picture here on the next slide, the ciliary escalator shows it's like shag carpeting, and I remember this type of carpeting in our house back in the 70s when I was a kid, very thick shag carpeting, and so that greatly increases the surface area, and so these cilia are able to trap microbes, and they're coated in mucus, and then move them up through the escalator. That's why it's called an escalator. It moves things upwards, out of the bronchial tubes, and enables us to then expectorate them and get rid of it. And you can see the lacrimal apparatus and how those glands work and the ducts and so forth on the surface of the eye, where bacteria and other microbes are constantly colonizing the conjunctiva. And just back to the ciliary escalator, if you smoke, stop. The chemicals in cigarette smoke destroy cilia. They stress the cells out. The cells then don't produce the cilia, and then you lose this natural filtration system that we have. And so highly recommend that if you do smoke, please quit, and if you don't, please continue not smoking. Some chemical factors. Now, moving on from the physical to the chemical, sebum contains fatty acids. Those acids have lower pH, and so they inhibit the growth of pathogens and fungi. Our skin has a low pH already of 3 to 5 due to the fatty acids that are within the sebum and lactic acid as well that's there. And so this low pH inhibits many bacterial species. Many of them prefer to live in the neutral zone of the pH scale, so around 6.5 to 7.5. So a pH of 3 to 5, that's awfully low for bacteria to tolerate. So that normally takes care of them being able to colonize our skin. Lysozyme, an enzyme, it's ubiquitous within our body. It's found in perspiration and our tears, saliva, the mucus we produce, and tissue fluids. Breaks down the cell walls within bacteria, especially gram-positive bacteria, as it's capable of breaking down peptidoglycan. Gram-negative has an outer membrane that's pretty complex, and lysozyme is not as effective against that outer membrane within gram-negative bacteria. And our gastric juice has a pretty low pH, about 1.2 to 3. That destroys bacteria and many of their toxins as well. And that brings up a point where often it's not just the bacteria that are causing illness, which they often don't. It's the toxins that they produce, the junk that they produce and secrete from their metabolism or from part of themselves as well. And normally bacteria will not release any toxins whenever they're in low numbers. However, when their numbers get enormous, which in some cases doesn't take very long, they will form a kind of collective intelligence, and there's a whole system of communication that they carry out by the secretion of chemical compounds, and bacteria pick these compounds up, and it's kind of a language that they speak. It's kind of like hormones per se, where they communicate with each other and act as kind of one large organism. And they typically don't produce toxins when they're on their own, because a single bacterium just living within you is nothing. I mean, it can't do anything to us because in comparison, we're an enormously huge host, and so they kind of don't want to make themselves known or seen. However, when their numbers increase to enormous proportions, millions of them, billions even, they become this almost like a superorganism, and then they start communicating, and then through their recognition that there's a whole load of them there, they will begin producing toxins and releasing them. And then that's when we start to show the signs and symptoms of illness, is when their numbers have reached immense proportions, and then they begin releasing their toxins. That topic is discussed in a later chapter. Their mechanisms of pathogenicity, and that will be in our textbook, chapter 15. Some other chemical factors, transference, and I highlighted the Fe in transference to point out iron, the chemical symbol for iron. Iron-binding proteins in blood, milk, saliva, and tears that inhibit their growth by reducing the amount of iron. So bacteria require this iron, and they're after this iron. They want the iron that's within us. And so we have these proteins in many of our bodily fluids that capture and hold on, chemically bond to this iron, and are resistant to releasing that iron. And just a side note, too much iron, if you're taking an iron supplement, for example, you need to be careful because too much of it increases the risk of infection. Now, of course, it doesn't guarantee that there's going to be an infection, but it increases the risk of it because now there's more available iron for the bacteria to then get a hold of and utilize for their metabolism. So too much iron, and if you're taking iron supplements, just be aware of that. Can put you at a risk of infection. Mucous membrane cells and phagocytes produce antimicrobial peptides, which can cause cell lysis then as well for bacteria and cause them to burst, which leads to the reduction of their numbers, obviously. Okay, the next topic is looking at immunity itself and the cells and proteins that are involved in that, and I think that's a good place to stop for now. Like I said, I'll be putting out more parts in this video, but for now, that's a good place to end. And so I thank you for watching, and I hope this was valuable for you.